Okay guys, this video is going to be all about transition metal complex shapes, bond angles and isomers. Okay, this is for AQA A-Level chemistry. What do you need to know? So by the end of this video, you're going to be learning about these bullet points right here. This is taken directly out of the specification. All right, so I'm going to break it down step by step, but let's read through the specification and see what you need to know. So first off, transition metal ions commonly form octahedral complexes. Okay, we're going to take a look at what that is. And this is with small ligands, so H2O or water and NH3 ammonia. Next up, octahedral complexes can display cis-trans isomerism, okay? So hopefully you guys are well familiar with EZ isomerism. This is in the alkenes topic for organic chemistry. This is just a fancy version of EZ, really, that's related to transition metal complexes. And this forms with monodentate ligands, and then we get optical isomerism with bidentate ligands. Okay, optical isomerism, hopefully you're familiar with this as well. Similar to EZ, this is in the organic chemistry topic. Okay, so hopefully you're well familiar with what this is already. I'm not going to spend too much time on the fine details of this. I'm only going to go over the relevant information for transition metals, okay? And this is with bidentate ligands. Next up, transition metal ions commonly form tetrahedral complexes with larger ligands, Cl- here, this chloride ion, and then we get square planar complexes, okay? These are formed and can display cis-trans isomerism. So also you get cis-trans isomerism with octahedral and square planar, okay? Then you need to know a very specific example. You need to know how to draw it and what its uses are, okay? And this is called cisplatin. And this is the cis isomer of this platinum complex. We'll take a look at that as well. You need to know silver ions, okay? Silver ions, Ag+, these form the linear complex. This guy right here. Again, another organics concept from aldehydes and ketones when you're differentiating those two in a test tube, right? Good old Tollens reagent. Okay guys, so let's go through this step by step. Octahedral complexes. This is again just straight out of the spec, okay? We need to know that they form octahedral complexes with small ligands, so water and ammonia. Okay, so what is an octahedral complex? A lot of students struggle with transition metals, right? It's no different from year one bonding, okay? You've got octahedral, tetrahedral, square planar, and linear. These are exactly the same. There's no crazy difference. It's just that you're going to have a transition metal at the center and it's going to be a complex. So I'm going to show you how to draw that. Now, I'm going to use the example of cobalt, okay? Good old cobalt 2+, and this is going to be our central transition metal in this case. Now, I'm going to use a ligand of ammonia as our example. If you've watched my video of every ligand substitution reaction you need to know under the transition metals topic, you should know the equation for this. But in this video, I'm going to switch things up and we're going to go over the shapes and the isomers. So how do we draw an octahedral complex of cobalt 2+ surrounded by 6 ammonia ligands, all right? So I'm going to start just by showing one, right? We've got NH3 right here. As you should be aware from my previous video, there's a lone pair on this nitrogen, right? And it forms a coordinate bond with the central transition metal, which previously I described as showing as an arrow, okay? And you'll see this in your textbooks, online resources, stuff like that. You want to completely ignore that essentially when you're answering exam questions when they tell you to draw the shape. You always want to show the geometric position of the bond, which is either shown as a line, so a straight line just signifying a bond right here, and then the 3D oriented bonds, okay? So you've got a dashed line like this, signifying going away from you, so going into the page in a 3D format. And then the third one is a wedge, okay? So a wedge, just like a triangle, and then colored in pretty much bold right here. And this signifies something coming towards you. Okay, so this is the 3D orientations you need to be aware of, and you always want to draw the complexes in this way. All right, so let's draw an example. So I'm using cobalt as my example, but this can change for any sort of transition metal in the topic, right? So we're gonna have our bond here and our bond here. This is just how you want to draw it, okay? You want to draw the ligand that's above and below the transition metal, just as those two straight lines, okay? Above and below the plane. Now, what we're going to have is you have two ligands going away from you on either side. Okay, so we're going to have NH3 over here and NH3 over here. Now, I'm going to draw this backwards to signify where the bond is actually onto. This bond is on the nitrogen. It's not on the hydrogen because the nitrogen has the lone pair of electrons that is donating to the transition metal to form the coordinate bond, right? And then all you have to do is show the other two bonds right here as coming towards you. Okay, are we done? No, we're not. Now, when you're drawing these complexes, even though this is a correct shape, you also need to show the square brackets to signify that it's a complex, and you need to put the charge in, okay? So all of these ligands right here are neutral. I said I'm using the cobalt 2+, so we're going to chuck a 2+ at the top right. Okay, that's our structure done, guys. Simple as that. Now, this is for an octahedral monodentate complex. You can swap these ammonias out for water molecules. That's completely fine. And just keep in mind, whatever the center is, you need to keep an eye on the charge. So if this was a 3+ transition metal, you'd get rid of this and just put 3+ right here. Okay, that's all you need to do. But just really pay attention to these bonds that are going away from you, stick them at the back, and then bonds towards you, stick them at the front, okay? Just realize that this is above the cobalt, this is below the cobalt, and then these four right here, if I draw like a dashed line around it, these are in the same plane, okay? So this is like flat. You can think of this as a flat plane. If you put like your hand in front of your face, and then this is above your hand, this is below your hand, okay? It's really hard to describe and explain without using like Molly-Mod kits or seeing it in a video format, but I'm trying my best in 2D drawing it out, okay? But just, I'm not going to go into too much detail around the orientation, but this is how you want to draw it. All right, octahedral, what is our bond angle? Exactly the same as year one, guys, 90 degrees, okay? There's 90 degrees between this and this, okay? And there's 90 degrees between this and this. There's 90 degrees between this and this. It doesn't really change. It's always 90, okay? Now, another thing you have to keep in mind is you can actually also get 180 degrees, okay? So, for example, the bond angle of a straight line. Where do we see that? We're going to see that going across the molecule, and we'll explore this a little bit more when it comes on to cis-trans and optical isomers in octahedral complexes, okay? So, for example, if we go from here all the way to here, this is directly across, so it's going to be 180 degrees, so just the same as a straight line. You're going to get exactly the same thing happening here and here. Okay, so just keep that in mind. It's 90 degrees between each ligand, but you can also get 180 degrees, okay? Now, what is the coordination number here? 6. Okay, I went through coordination numbers and coordinate bonds in detail in my previous video. Every ligand substitution reaction you need to know, so if you're a bit confused, check that out. Okay, so we've gone through the shape, how to draw it, what the bond angle is for octahedral complexes. Now we need to talk about the isomerism, so cis-trans. So what is this? So we have EZ isomerism, right? We have an alkene carbon-carbon double bond, and then if it's on the same side of the molecule, it's going to be an E isomer. So if the two priority groups on the same side, it's an E isomer, and if it's on the opposite side, so like here and here, going across the molecule, this is a Z isomer. Very, very similar for these transition metal concepts, but you don't have a central carbon-carbon double bond. Instead, you have a transition metal. So let's look at how it's different. I'm going to quickly draw out an example of a transition metal. I'm going to go through the cis isomer, and then we're going to switch it up and look at the trans isomer. You need to know how to draw these and answer questions surrounding it, okay? All right, so I'm going to draw chromium this time as our example, chromium 3+, okay? So I'm going to have again, bonds, straight bonds above and below the plane. And then what we're going to do is we're going to draw our bonds going away from us and bonds coming towards us. Now, I normally like to draw the bonds straight away, and then I can just chuck the ligands in where they need to go. Okay, so octahedral complexes. Previously, let's say we use an example of a hexa aqua complex. Okay, so 6 water molecules. Let's draw that right now. All right, so let's draw on these ligands. So H2O. I'm going to switch it up here to be OH2, just so that signifies where the bond is actually on. Again, H2O, H2O, H2O. Again, there's going to be square. I'm going to draw the square brackets quite far away here. You don't have to do that, but just so it leaves me space in case I need to change anything. All right, so this is going to be 3+, like I said, chromium 3+, right? Now, what we need to keep in mind is this is the hexa aqua complex, okay? The only instance that you're going to get cis-trans isomerism is where you switch out 2 of these ligands for something else, and it's normally going to be chloride ions. That's the ones you need to know for AQA, right? So you're going to get 2 lots of chloride ions coming in, substituting 2 of these water ligands, And that will allow you to get cis-trans isomerism, okay? So let's draw an example here. Let's get rid of this water molecule right here and this water molecule right here and replace that with 2 chloride ions. Oh, I don't know why I drew the negative charge. You don't want to show the negative charge on the ligand, okay? Because it's already donated that electron. Now, the charge here is going to change. You really need to keep that in mind. It's no longer a 3+ because we've introduced 2 negative ions. So you essentially just need to minus 2 from this, okay? So it's just going to be a 1+ charge. All right, so I got rid of that. Now, what type of isomerism is existing here in this molecule, or this complex, I should say, that I've just drawn? Cis, okay? Now, very similar to EZ isomerism, E isomer is the exact same thing as cis isomer, okay? Then over here, very similar to EZ again, Z isomer right here is just trans. Actually, I'm going to put trans here because you need to call it trans, okay? Really try and avoid using that EZ terminology for transition metals. They don't really want to see that. They want to see cis-trans, okay? So don't use EZ, use cis-trans, but understand it means exactly the same thing. So let me draw out a trans example, and then I'll explain how to differentiate the two and what you need to do if you need to draw out the 2 different isomers. Okay, so the way that I like to think of it is if the ligands, the 2 different ligands, so we have 4 of the same, 2 different, that's always going to be the same for cis-trans, okay? You're going to have 2 different ligands coming in. If these are next to each other in the molecule or adjacent to one another, it's going to be cis. Whereas, let's say we switch this up, made this the chloride ion at the bottom, and this H2O molecule again, a ligand up here, this is now across the molecule, so it's going to be a trans isomer, okay? This is the way I remembered it, and it never failed me, okay? So in my previous example, I said, what is the bond angle here from our previous slide? The bond angle here would have been 90 degrees, right? And then what is the bond angle here? 180. Okay, so the way that I like to think about it when I did my exams is that if 2 ligands are adjacent, they are within 90 degrees of one another. Whereas if they're trans or across the molecule, they are 180 degrees apart. Okay, that is the bond angle here. So let's say we switch this up because you're not going to always get it this simple. Okay, you're going to see some questions where it's more complicated. It won't always be like, okay, one's up here, one's down here. You may get it different, right? So let's say this was the chloride ion right here. I keep going to draw the negative. Don't draw the negative, just keep that in mind. So this also is 180 degrees. Then obviously if we chuck our water molecules back in, all good to go, right? Again, 180 degrees. Now, let's say we change this up to be the 2 chloride ions here and here. Okay, this is 90 degrees apart again, so they're adjacent, therefore it's cis, right? I'm not going to draw in the water molecules every time, but let's do another example. Let's say one was here and one was here. Is this cis or is this trans? Okay, obviously imagine there's water molecules still here. Now you may be tempted to say, okay, this is trans. They're across the molecule. Okay, what is this bond angle? 90 degrees. Okay, so this is also cis. Just keep that in mind. They don't talk about bond angles within isomerism in the textbook or on online resources, but I find that think of it in this way, in this 3D format. Are they adjacent to each other? What is the bond angle? That will allow you to determine 100% of the time if it's cis or trans. Okay, just keep that in mind, because if you think about it, the 3D orientation can get a bit confusing sometimes, especially in 2D drawn format like this. So these, I would say personally, when I was doing my A-levels originally, this would confuse the hell out of me because I would think that these are across the central transition metal, but it's not the case. Okay, these are in the same plane and these are adjacent to one another. Okay, 90 degrees all the way around here. Okay, so just keep that in mind. That was messy as hell, but let's move on to bidentate ligands. All right, this is where we get introduced to optical isomerism. As I said, you should be well aware of this from organics, but you need to know that this occurs when we're dealing with bidentate ligands. Okay, so I've got rid of all of the cis-trans isomerism stuff to do with octahedral. Let's look at bidentate ligands this time. Now, there's two you need to know, and I went into them in great detail in my ligand substitution video, but I'm going to cover them real quickly here because we need to know the structures, okay? We need to know how they bond onto that transition metal center and how to draw it. So what are the two you need to know? You need to know ethane 1,2-diamine. And you need to know ethane diurate. Okay. Now, when you're drawing these out as equations in your exams, you just want to show it like this. Okay. Ethane diurate is just going to be NH2, CH2, CH2, NH2. Okay. Ethane in the center, 1,2-diamine. And then ethane diurate, you want to draw it simply as C2O4 2-. Okay. This is a 2- negatively charged anion. So you're going to get a change in oxidation number in your equations, okay? Just remember that. How do we draw these guys? Let's look at an example of ethane 1,2-diamine, and then we'll do an example of ethane diurate after. Okay, so I'm going to use an example of Fe3+ as my center. Okay, but this can change up. Now, what is the structure of ethane 1,2-diamine? So you're going to have the NH2 right here. This is going to bond onto an ethane hydrocarbon chain, and then come back down to BRNH2 again. Okay, now remember I said the lone pair is on the nitrogen. This is going to form bonds with the central transition metal. Okay, so just remember this structure, and all you need to do is you need to draw it around this center 3 times. Okay, so what I recommend doing, as I said in my previous section of the video when I was doing the cis-trans isomerism, draw the bonds first. Okay, I find this the easiest way. So drawing our 2 straight line bonds for above and below the plane, and then we've got our dashes and our wedges. Okay, that is the way that I find the easiest. And then all we have to do is slot these bidentate ligands around this complex. Okay, if you're not sure what bidentate means, I went through it in my other video, 2 coordinate bonds per ligand. As we can see here, 2 lone pairs, 2 coordinate bonds form. Okay, so just keep that in mind. Let's draw this around this molecule, okay? So you can slot them in anywhere you want, but when you draw the other isomer, okay, the enantiomer or the mirror image, you need to draw them mirrored, like perfectly mirrored. If you're a bit confused, I'll explain what I mean. So I'm going to chuck this NH2, CH2, CH2, NH2 on these 2 bonds right here. So let's draw that out. So we have our NH2, CH2, CH2, NH2. You can do it skeletally if you want. So you can have NH2, NH2 like that. There's obviously a carbon here. But I like to show all the bonds when I'm explaining things. And then I'm going to slot the other one up here. Okay, so we're going to have an NH2, CH2, CH2, NH2. Okay, a bit messy, a bit squished, but that's all you need to do it as. Okay, just make sure that the bond goes on the nitrogen and not the hydrogen. So this one's a bit awkward, but hopefully you see the idea here. Then all we have to do is slot the last one down here. So we have NH2 here, we have another NH2 here, CH2, CH2, and then that's bonded on here. All right, and this is our bidentate octahedral complex, okay? So what's the last thing I need to do here? Square brackets and the charge. Okay, at the beginning, I said it was a 3+. What is the charge on this ethane 1,2-diamine? Neutral, so it's just going to be 3+. Okay, so let's get rid of this guy right here and delve into what an optical isomer is. So we know how to draw it. As I said, you can switch this up. So you can do the ethane 1,2-diamine between these 2 bonds instead, or you can do it between these 2 bonds. It doesn't really matter. Just make sure when you do your mirror image, that is what's formed, okay? Now, another thing that may not be super clear here is when you're producing optical isomers, you need 3 bidentate ligands, okay? You need all 3 to be bidentate. You can't just have one bidentate and the rest monodentate. They need to all 3 be bidentate, okay? So just keep that in mind. I'm not going to go into crazy detail about optical isomerism in this video. I'm just going to tell you that all you need to know is that these are non-superimposable mirror images of one another, also referred to as enantiomers, okay? You're going to get 2 enantiomers. I think that's how you pronounce it. Enantiomers, I'm not too sure, but that's how I always said it. whatever you want to say is fine as long as you get the spelling right and you can explain it in your exams. So that's all you need to know, non-superimposable images. Let's draw it right now. So I'm going to draw an imaginary dashed line here. Don't want to do this in your exam, okay? I mean, you can, but yeah, try and avoid this if you can, but it helps me sort of explain it better to you guys. So let's copy and paste this over with the bonds, and then we're going to slot the bidentate ligands or the arrangement of the bidentate ligands slightly differently so that it's a perfect mirror image. All right, cool. So we've copy and pasted this in, still an iron 3 plus center. How are we going to draw this? So you literally just want to mirror it. So as you can see, this is on the right-hand side of the complex. So in the mirror image, we have to mirror that and put it on the left-hand side. Hopefully that makes sense to you guys. So we're going to have an NH2 here, NH2 here, and then we just have to draw the CH2, CH2, and bond that on. Okay. On this side, it's at the top left, so naturally we have to do it at the top right. Hopefully you guys are just seeing here, it's a mirror image, that's all you have to do. Right? This is at the bottom left, right? So we're going to do it at the bottom right. It's literally that simple. Okay, so this is our enantiomer or our non-superimposable, let me write that down, non-superimposable mirror image. It essentially just means they cannot be placed on top of one another when you rotate these bonds around. I'm not going to go into detail. You should hopefully be aware of this from organics, but this is all you need to know. This is our keyword here, non-superimposable mirror image of one another. So let's say all we did was redraw this. Okay, let's say we redrew this with this at the top left, this in the middle right, and this at the bottom left, and you drew this twice. This is not a non-superimposable mirror image. Okay, these are not optical isomers. You would just be drawing the same complex twice. Okay, really try and avoid that. So for example, let's say we switch this around and this one was drawn for you in the exam already by AQA and they said, draw the non-superimposable mirror image. You would say, okay, this is at the top right. How do I mirror that? Draw it at the top left. Okay, that's how you want to do it as a mirror image of one another. And you would just follow that procedure for whatever shape you're given. Main thing to remember here is you need 3 bidentate ligands in an octahedral complex. Okay. And this will produce non-superimposable mirror images of one another. Not sure why I put the dash there. The dash should be between the non and the super. Just keep that in mind. All right, so some of you guys might be stressing out here, not really understanding what's going on. It is complicated, okay? Without 3D Molymod kits or something to physically show you in front of your face where these are arranged, just remember, you don't need to understand it. You just need to be able to draw it, okay? So just mirror those guys up and you'll be completely fine. Now, we've covered ethane 1,2 diamine. You also need to be aware of ethane diurate, and it's exactly the same process, okay? I'm not going to overcomplicate it for you guys, exactly the same process. So I'm not going to waste too much of your time and go through redrawing the entire thing, but you do need to know how to draw it and how to draw the mirror image. So let me rub all these out and we'll focus simply on one bond type of the ethane diurate and mirror that, and you'll just replicate exactly the same thing that you would do with ethane 1,2 diamine, but just switch it out for the C2O42- ligand. All right, cool. So let's draw this out. Now, one thing I'm going to say is you can draw this skeletally to make things easier for you, and the charge will change. Okay, what is the charge going to be? We started with a 3+. We're adding 3 lots of 2-, which is exactly the same thing as 3 - 6. Okay, so you're going to get a 3- charge. Just keep that in mind and you'll be good to go. So let's write that down then. Going to be a 3- here. And then again, what you want to do, I advise just starting by drawing the bonds. Remember, in the exam, you kind of want to fill these in, but I'm just being lazy, so I'm going to leave it just as triangle wedges right here. Now, I'm going to draw one structure, okay? How do we draw this? The oxygens are the ones donating the lone pair, okay? So our structure is going to be the 2 oxygens. Let me draw it over here quickly. So we'd have oxygen, carbonyl, another carbonyl, oxygen, lone pair on these two guys, and these have the negative charges. Okay, that's where the C2O42 minus comes from. It's on these oxygens with the lone pairs. So these would technically be carboxylates, all right? So what we're going to do here is draw this out, real simple stuff. So we're going to do exactly the same thing. CO carbonyl, oxygen, okay? And you just want to draw that out 3 different times, okay? Now, as I said, you can do it skeletally, which I'll show you in a bit, but let's just draw the mirror image of this, right? So as I said, you just want to mirror it. Where in this molecule is this ethane diolate? In this instance, it's at the top right, okay? We've got one in the up plane and one in the away from us to the right plane. So what you want to do is you want to mirror that and use these two, okay? It's going to be on the top right here, so you have to mirror that and put it on the top left. So you can have O, O, C, C, carbonyl, another carbonyl, okay? That is our mirror image. Now, obviously, let's say we had one here, you'd have the other one here, the other one here. You want to mirror that. This is the bottom right, so it's going to be at the bottom left. This is at the middle left, I would say. So you're going to put it in the middle right. Okay, simple as that, guys. Just remember the charge and the orientation. Now, skeletal, let's go over this real quick, just like with the ethane 1,2-diamine. Let me rub this out. This is ethane diolate. Don't get confused there. Let's rub this out and replace it. Ethane diolate. All right, cool. So skeletal, how would we do this? You want to draw it like that. 1 carbon here, 1 carbon here, right? And then you just have to draw the double bonded oxygens coming off of it. Okay, this might make things a bit less messy for you, and you could structure it in this way. This is completely accepted. If you don't really understand skeletal, just draw it in this format and you'll get the marks. Okay? Again, these are non-superimposable mirror images of one another. When you do them opposite like this, imagining a mirror in the middle, and this only forms when you have 3 bidentates. Okay, if this was bidentate and then you had like a H2O here, 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 and here, you're not going to get optical isomerism, okay? Because these are single bonds. There's no restricted rotation because these 2 bonds here have, I'm not going to go into detail here, but essentially these have restricted rotation now because they're sort of fixed. These 2 bonds are now fixed to one ligand, so you cannot just flip them around and rotate it like you can with single bonds, okay? But I'm not going to go into any more detail, just focus on this key terminology, non-superimposable mirror images of one another or enantiomers, and you'll be completely fine. Whew, all right, we're getting through this. Tetrahedral, okay? Transition metal ions commonly form tetrahedral complexes with larger ligands, all right? I went through this in my ligand substitution video. These guys are larger in size than water and ammonia, so you can only get 4 coordinate bonds forming or 4 ligands around the central transition metal. That's just how it works. How would you draw these structures, okay? I'm going to use the example of copper chloride, okay? CuCl, 4 of these guys, square bracket it up. What is the charge? 2-. Okay, this is our copper chloride complex. How are we going to draw this? What we want to do is we want to start with the central transition metal center and then draw the bonds, okay? So there's not 6 bonds here. It's not octahedral. It's going to be tetrahedral. So how do we draw that? So you're going to have one here. You're going to have the wedge coming out and then the trailing dashed bond signifying it going away from you. Okay, you can flip this up. You may not see it always in this way. You may see this straight bond to the right and this flipped around. But as long as you draw 1 bond straight up, and then you're going to have 1 bond at the bottom somewhere, whether it's at the left or the right, doesn't really matter. And then showing 1 bond coming towards you by the wedge and 1 bond going away from you as the dashed line, okay? Not too bad. So where we're going to slot in our chlorides, literally just chuck them on like this. Cl, 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 okay? Not too bad here, okay? Last thing, square brackets, and the charge. What is the charge going to be? 2-, I've already said here, okay? This will change. Just remember, what you do is you do the transition metal, whatever that charge is, and then you do -4, okay? Why do we do -4? It's because each of these chloride ions has a 1- charge, okay? Just remember that. So collectively, it's going to be 4- or -4, and that's how you would get the actual charge of the complex. What isomerism do we get here? Nothing. Okay, there's no isomerism for these tetrahedral monodentate complexes. That is going to take place in square planar complexes. So let's take a look at them right now. Actually, quickly before we move on, I completely forgot bond angles. Okay, what is the bond angle here? Exactly the same as year one. Doesn't get any crazier with transition metals. 109.5 degrees. Okay, just remember that and you'll be completely fine. All right, square planar. How are we going to draw this and what example do you need to know? Cisplatin. Okay, you need to know the structure of cisplatin and you need to understand that this is the cis isomer of this platinum complex, which I'll draw in a second, but you can also exhibit the trans isomer of this complex, okay? All right, so all you want to do here is just understand that platinum is going to be at the center and it's surrounded by 2 ammonia ligands and 2 chloride ligands. So let's just draw that out. And the way that I advise doing this, again, as always, start with the bonds, right? So we're going to do 2 wedges coming towards us and 2 dashes signifying the bonds are traveling away from us in the 3D orientation, right? So what we're going to do here is we're going to draw in our ammonia ligands right here at the top. So NH3, NH3, and then let's do our chloride ligands right here. Cl, Cl. Okay. So this is cisplatin. Let's draw the trans version and you can see how they're different. Right, so I've copied this out just showing our bonds and we're going to look at how you would draw the trans isomer. But let's go over this one more second. So again, there's square brackets here. Do you need to show that? No, you do not, okay? There's no charge here, so you don't need to show it in the structure. You don't really need to show the square brackets here because it doesn't have a charge, okay? The platinum is 2+, there's 2 lots of 1-, so it just becomes neutral. Okay, so just keep that in mind. Now, very similar to EZ isomers, this one's a lot more simple, right? So what you can do is you can think of this central transition metal as the CC double bond. And then if things are on the same side of the molecule, it's going to be what? Is it going to be cis or is it going to be trans? It's going to be cis, okay? These 2 chloride ions are on the same side. The ammonias are on the same side. So it's going to be cis, right? Now, if we switch this up and said, okay, one chloride ligand is here, 1 chloride ligand is here. And then we have an ammonia here, an ammonia here. These respective ligands are now across the molecule. Okay, so it's going to be trans. Okay, even though these are drawn on the same side like this, they can also be drawn here. So let's rub this guy out. Cl. Okay, these are now on the same side. And then obviously I left a chloride ion here, but you need to get rid of that and replace it with an NH3. Okay, so just remember, if they're adjacent to one another on the same side, whether it's here, 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 it doesn't really matter. As long as they're next to each other on the same side of the molecule, of the complex, I should say, it's going to be cis isomer. Okay, and this is going to be trans isomer. And if I haven't mentioned it so far, you should really know this from alkenes and organics. This is a type of geometric isomerism. This comes under the umbrella of geometric isomerism, which is a type of stereo isomerism. Okay, optical isomerism is also a type of stereo isomerism. Okay, just keep that in mind. All right, guys. So what is the bond angle going to be here? 90 degrees. Okay, remember these are in the same plane. You can essentially think of it as 360 degrees for the whole thing. Slot that into 4. It's going to be 90 degrees between each ligand, right? Hopefully that makes sense. Just remember that same side of the molecule, cis, opposite sides, trans. Okay, keep that in mind and you'll be completely fine. One more thing to mention is that this is an anti-cancer drug, okay? And you only get the anti-cancer activity with the cis isomer, okay? If we're using a compound that's the trans isomer, you're not going to get the same DNA binding or anti-cancer activity that the drug's intended use has. So you're not going to get the same action inside the body, okay? So you're only going to want to use the cis isomer for these cases, for this medication. All right, last one here, Ag plus forms this complex. This is a super easy one, so let's fly through this, right? So we're going to have our Ag at the center, 2 bonds either side. Then we're going to have our NH3s, okay, our ammonia ligands right here, NH3. Square bracket this guy up. What is our charge? Ag is 1+ charge. So our silver ion here, NH3 is a neutral, so it's going to be 1+. All right, simple as that, guys. This is linear. What is this bond angle? 180 degrees, the angle of a straight line. Okay, just keep that in mind. This is Tollens, or the active complex within Tollens reagent. Okay, what do we use? What happened to the end there? Reagent. Let's redraw that. Reagent. Okay, I'm writing too fast here. What is the common use of this? To identify an aldehyde. Okay, you're going to get silver mirror. I'm not going to go through that in this video. You don't need to know that. You just need to know that for organics. Okay, but keep in mind, this is the active complex intolerance reagent. All right, sick. We've gone through everything. Let's tick this off. Make sure we've gone through it. Transition metal ions commonly form octahedral complexes with small ligands. Done that. Octahedral complexes can display cis-trans isomerism, which is just a special case of EZ isomerism. With monodentate ligands, did that. And optical isomerism with bidentate ligands, did that, okay? Transition metal ions commonly form tetrahedral complexes with larger ligands, chloride ions, and this is because only 4 can fit around. Our coordination number is 4, not 6. Square planar complexes are also formed and can display cis-trans isomerism. Went through both of those things just now. Cisplatin is the cis isomer, easy peasy. Ag+ forms a linear complex as used in tolerance reagent. Super, super easy. And we also did all the bond angles here, which you also need to know. Now it's time for some extra stuff. Skill development and practice questions, okay? The specification outlines in the second column areas of skill development. So let's look at that right now. Right, so this is something you're going to have to do on your own, guys, all right? I'm not going to go through this. Hopefully it's something you can apply directly from this video as well as the upcoming practice questions. But let's just take a look at these. You need to understand and be able to draw the shape of complex ions. Hopefully through this video, you can be able to do that, right? Next up, you need to understand the origin of cis-trans and optical isomerism. Optical isomerism, 3 bidentate ligands, all right? Cis-trans is going to be square planar and octahedral when you've got 6 monodentate ligands, 2 of the same, 4 of the same, okay? You're going to have 2 across or 2 adjacent. This is where you get cis-trans in octahedral complexes. And then square planar is just going to be opposite in the complex, right? You need to be able to draw these cis-trans and optical isomers, which I've gone through as well. And you need to be able to describe the type of stereoisomers shown by these molecules and complexes. Remember, stereoisomers, I said, can be broken down into what? Do you remember? Geometric and optical. All right, just remember that. Remember geometric. Remember the definition of this. You're going to learn that in organics. I'm not going to go through that in this video. Optical, just remember non-superimposable mirror images of one another, and you should be fine here. Now, the one thing I haven't actually mentioned, which is important, there's no chiral carbon, okay? This is not organics. Chiral carbon, you've seen that all before, where there's 4 different groups bonded onto the carbon. Completely ignore that for inorganics, all right? Optical, just refer to those non-superimposable mirror images, all right? And you'll be good to go. All right, cool. Let's go through some practice questions, okay? This is the perfect opportunity to do some active recall. Take what you've just learned and apply it to some questions, okay? So pause the video, attempt these questions as I go along. Do your best, okay? Really push yourself and identify where you're lacking knowledge, okay? So let's pause the video and then come back to this and see how you did. All right, shapes. Easy peasy, guys. What is this? Is the active ingredient in tolerance, or the active ingredient? It's not a food. Active complex. All right, so this is going to be linear. Real easy, which has got 1 ligand either side. What is the shape of this? Octahedral. Okay, perfect. What is the shape of this? Tetrahedral. Okay, just testing your knowledge here with some really easy stuff, but hopefully you guys are aware of this. As you noticed, I chucked in a different transition metal here, nickel. It's not as simple. They may test your knowledge, push your knowledge. You may not be familiar, but just realize that this is always going to be tetrahedral, okay? All right, question 2. What type of isomerism would an octahedral complex with bidentate ligands display and why? Okay. So what isomerism is produced? Hopefully you guys remember. Optical isomerism. Okay, my handwriting's getting worse and worse as we go. Why is this? Okay, this is really important. It's because the arrangement of the coordinate bonds, the 2 coordinate bonds for each bidentate ligand, can lead to non-superimposable mirror images of one another, or enantiomers being formed. Okay, remember that key terminology, non-superimposable mirror images. All right, done. This is because the arrangement of the 2 coordinate bonds for each bidentate ligand can lead to non superimposable mirror images, okay? Enantiomers, a bit of a weird word, being formed, okay? Just remember this key terminology that I've highlighted and you should be completely fine. All right, question 3. The FeH2O4Cl2 plus complex exists as two isomers. One isomer is shown below. You need to draw the structure of the other isomer and state the type of isomerism as well as the bond angle. Okay, can you guys do this? Pause the video, see how you do. All right, cool. I've switched this up. I've put them in purple here. So these were two chloride ions right here originally, these chloride ligands. I've switched it up and they are now what? What type of isomerism is existing here? Cis-trans isomerism. Okay. Why is this? It's because on this side, they are adjacent, or you don't want to really say this in your response, but just think of it as these are 90 degrees apart. Okay, these are adjacent to one another. And here, these are 180 degrees or across the molecule. Okay, equally, let's say you wanted to do it differently. You could have done it across this way. Okay, so you could have put a Cl here, and then you could have moved the H2O to be up here. Okay, hopefully that makes sense to you guys. I chose to do it top and bottom, but you could have done it like this as well. Both of those are going to be the trans isomer across the molecule, or the way I like to think of it, 180 degrees apart. All right, we've done that. Bond angle, I kind of also included it here, 90 degrees, okay? 90 degrees bond angle and 180. Remember, 90 degrees here and then 180 all the way across. Okay, that is our bond angles here. 90, 180, not too bad. All right, question 4. Let's do this. Pause the video, attempt it yourself, see where you go wrong, hopefully get it right. Platinum can form complexes with ammonia and chloride ions and exhibit cis-trans isomerism. So this isomerism again, cis-trans, right? Cisplatin is commonly used as an anti-cancer drug. Draw the trans isomer and state the bond angle. All right, so hopefully you remember how to draw this. All right, so let's start. Platinum in the center. What do we do next? We're going to draw in our bonds and then slot the ligands in the right place. So 2 dashed to show going away from us, 2 towards us, shown by the wedges, right? Again, you probably want to color these in, but I'm just being lazy, okay? So let's draw in our ammonia molecules and our chloride ions, right? How do we do this? So it's asked us for the trans isomer. What does trans mean? Opposite the molecule, okay? So let's draw in our ammonia. So I'm going to have NH3 here. Would we draw the NH3 here for a trans isomer? No, we would not, because that means that they are within 90 degrees of one another or next to each other or adjacent in the molecule. You're going to have to draw them across, okay? So let's draw in the chloride ions right now. Let's do it a nice blue, Cl, Cl, done, okay? Easy as that, guys. This is the trans isomer. What is the bond angle? Kind of gave it away already. 90 degrees. Okay, 90 degrees between each ligand. In this one, you don't really want to mention 180. I'm not going to lie to you guys. Just focus on 90 degrees. But obviously, you can think the distance between two ligands is going to be 180 when they're across the molecule like this. All right, last question. Question 5. Draw the two isomers of a complex containing cobalt-2 and ethane dioate ions. You remember what type of ligand this is? Is it mono or bidentate? And then we need to name the type of isomerism and state the bond angle. All right, cool. So pause the video, attempt this, see where you go wrong. All right, so I'm going to draw this out from scratch rather than just like pasting it on the screen for you so you can see again exactly what I do. Central transition metal is a cobalt-2+. So we'll take a note of the charge here. I'm going to chuck on all my bonds, okay? Dash line for away, wedge towards us. I'm going to replicate that on the left side of the molecule as well, right? I'm rushing this a little bit, so it might be a bit messy. Ethane dioate, okay? What does this look like? Remember, all of these are oxygens, okay? We've got an oxygen on every single one of these bonds right here because the oxygen is donating the lone pair, okay? Cool, we've drawn in our oxygens. What do we want to do now? Just draw the rest of the ligand, right? So do you remember how to draw it? So we've got 2 carbons here for our ethane portion of the ligand. Don't know what happened to that bond. Let's redraw that, guys. And then we're going to have our carbonyl group right here. This is the dioate portion. So 2 O8s OH is just this Q minus, okay? Carboxylate, and there's 2 of those. So this is our ligand right here. I've chosen to draw it here. You can draw it wherever you want as long as you slot 3 around here. Okay, and again, I'm going to draw this one right here. I'm going to draw it actually as the skeletal formula, so we mix things up. Don't do this in your exam, okay? Keep it uniform. If you draw one skeletal, draw them all skeletal. Okay, so CO, CO, and then I'm going to do that right here as well. Just remember, each of these is a carbon, right? Okay, cool. Are we done? This is our structure. Are we done? No, we're not. We've got to show square brackets and the charge. Remember that, guys. Square brackets and the charge. What is the charge here? Cobalt 2. What is the charge on each of these ethane diol ions? 2 minus, right? So we've got 2 minus plus, how many of that? 3. 3 lots of 2 minus. So it's going to be the same as 2 minus 6 equals minus 4. All right, so that would be our charge here, 4 minus. Let's rub this out. And let's draw them. I nearly gave it away then. I nearly said the key word. What is the type of isomerism that would be exhibited here? We have 3 bidentate ligands in an octahedral complex. Optical. Okay, optical isomerism. Just remember, this is a type of stereo isomerism. So we've named the isomerism. We need to draw it. Okay, we need to draw the other isomer. So how do we do that? Remember, mirror image, guys. So what we want to do is, I'm going to teach it like this with a dashed line. Don't do that in your exams. Just keep that in mind. Let's draw the mirror image. So again, I'm just going to do cobalt at the center. Draw all of our bonds on. Okay, dash going away, wedge coming towards us on either side. And then we're just chucking the ethane diol. So on here, where is this, guys? This is in the middle right. So what I'm going to do is mirror that to be in the middle left. So oxygen, oxygen. Going to keep it skeletal here just to make things a bit quicker for me, but feel free to draw it out like this. That's completely fine, guys. And then here it's at the top left, so I'm going to swap that over, do the mirror image to be the top right. Okay, cool. This is bottom left, mirror image, bottom right. Okay, it's literally that simple. Don't overcomplicate it in your head. It's not that bad. All right, cool. We've done the mirror image. All you got to do, square bracket this guy up. Same charge here. Done. All right. What is the bond angle? There's 2 actually. Okay, remember there's 90 degrees between these ones. Or this one, for example. Any of these, same plane is going to be 90 degrees. Or between the up and the center plane, right? And the other one, what is the other one? 180. Okay, so for example, across here, going to be 180. So that would be our answer, 90 and 180 degrees. That is our bond angle. All right, guys, that's the end of the video. It's a real long one. Hopefully you stuck it in there. Hopefully you found those questions really useful. If you did like the video and you found it helpful, give me a like, share to any of your friends that are struggling. It really helps the channel out. Hopefully you've seen that it's not that complicated, okay? Just involves a bit of practice. I quite enjoy this. The shapes and learning all this stuff was a bit more interesting than just memorizing equations and colors. It's a bit more involved, so hopefully you feel the same way. If not, it's all good. Paper 1's over soon. Remember, this topic can also come up in paper 3, so just keep that in mind. This is everything you need to know for the shapes and the isomers. And remember, guys, skill development, okay? Practice these 4 things because they will require you to be able to do this in your exams. With that being said, guys, best of luck in your upcoming exams and revision. Until next time, peace.